still nothing. Okay. So 39 f of x equals x plus 2 sine x. So we're talking about what values of x. We can also determine the points, and I would like to add that for what points, if they exist, does the graph of f have a horizontal tangent. So horizontal tangent. Okay, so here's a situation. This function has a horizontal tangent. Definitely wherever there is a peak, that's a horizontal tangent because the slope is 0. And here's another point where the tangent is horizontal because the slope is 0. Okay? So any other tangent, for example, this one has a positive slope, this one has a negative slope, this one has a positive slope, and so on and so forth. But the horizontal tangent means slope 0. Every horizontal line we know has slope 0. So any suggestions? Will anyone say anything? How do I proceed? How do I determine one or more points? I don't know. Where the function has a horizontal tangent, what should I do?
Find the derivative and set it equal to 0.
Brilliant, thank you. So first, f prime of x. Can anyone give us f prime of x? Anyone other than Caitlin? She already told us what to do.
Say 1 plus 2 plus x.
Very good, awesome, brilliant. So now we have to set it equal to 0. Why set it equal to 0? Because we're talking about tangent that is horizontal. Good, so then I have to cosine x equals -1 or cosine x equals -1/2. And let me refresh your memory. So if we are looking at sine x, cosine x, and let's say we have pi over 6, pi over 4, and pi over 3. These are the main angles. That's all you need to remember, and you really don't even need to remember because it's so easy. 1/2, 1/2, the square root of 3 over 2, the square root of 3 over 2, and the square root of 2 over 2, the square root of 2 over 2. So you have to remember 3 numbers. 1/2, 1/2, square root of 3 over 2, both, cosine pi over 6 and sine pi over 3. And this is the easiest one, the same thing. So at this point, I know I'm talking about cosine, that is 1/2. So obviously, I'm talking about something in connection to pi over 3, for sure. Right? Because we're talking about cosine being this. And you can say, but what happens to the negative? In a minute. So now we have to look at the unit circle. And we have to identify where is cosine negative. Remember, cosine is measured here on the x-axis. So this will give us cosine. This will give us sine. So then if cosine is negative, can anyone tell us where is cosine negative? Which quadrants?
The second and third one.
Very good. Awesome. So remember, we are talking about pi over 3. So this reference angle has to be pi over 3. And of course here, the reference angle has to be pi over 3. Mandatory. Reference angle, reference angle. So we have 2 angles. This one, and we have this one, with the same reference angle. So cosine x equals -1/2. We should determine 2 options. Infinitely many, because the function is defined everywhere and it's going around based on sine. We're going to write all of them. So can anyone give us this angle? and then this angle. It's very easy knowing that this is pi. So pi minus pi over 3 will be here, and pi plus pi over 3 will be here. So what are the angles? And then plus 2 pi k, where k is 0, plus or minus 1, plus or minus 2, and so on and so forth. So what is the other option? So how much is pi minus pi over 3?
2 pi over 3.
Thank you so much. And how much is pi plus pi over 3?
4 pi over 3.
Very good. Good. That's awesome. Now I would like us to talk about a few limits. And I'm going back to the limit that we discussed last time. Anyone remembers the limit as x approaches 0 from either side from sine x over x? What did we discover this to equal to?
One?
Yes, 1. But this is the way, thank you, but this is the way we should remember this. Limit why? Well, what does this mean? It means that if this quantity is the same with this quantity and the same with this quantity, the answer will always be 1. Now, if any of these is not the same with the others, then the answer will not be 1. So let's take a look at a few examples. You can say, well, why do I need to remember that? I have now L'Hopital's rule. Who cares about this? Well, we do care. So let me just show a few examples. So let's start with, I'm looking at number 60. Oh, let me show. So I'm looking at problems 45 through 60. And I'm just going to start with this one. So limit as x approaches 1 from sine x minus 1 divided by x squared plus x minus 2. And you can say limits again. Yes, you will not get away from limits ever in math. Not in Calc 1, not in Calc 2, not beyond. Yes, limits will follow us everywhere we go. Okay, so what is the first thing we do when we calculate a limit? What is the first thing?
Plug it in.
Plug it in, awesome. Good, so where is the numerator going? So remember, this cannot be dropped till the last step. And this says, find the tendency of this function. The tendency, that's what this operator is all about. Good, so let's plug it in and see where is the numerator going.
0.
Very good. What about the denominator?
0.
Good. So there is hope. It's one of the indeterminate cases. We know 3 of them so far. Okay, we're going to add 4 more later on. Good, so if it's 0 over 0, then I know what happens in the denominator. So I know that the problem is x minus 1, right? So I will have to factor the denominator. Obviously, there is nothing I can do to the numerator. But I just want to refresh our memory on something. When we say that x approaches 1, we really mean that x minus 1 approaches 0. It's the same thing. These two are identical. When we say x approaches 1, we indirectly say x minus 1 approaches 0. So then limit, I'm going to write it in both ways. X approaches 1 for you to see what I'm doing. And in parentheses, I'm going to write x minus 1 approaches 0. So we can have it right there. There is nothing I can do to the numerator. But can anyone tell us what to do to the denominator? We already know one of the factors because we know the factor theorem. That is carved in stone. If I plug in a polynomial, if I plug in 1 and I get 0, x minus 1 is a factor. Guaranteed.
X plus 2.
Very good. So coming back to this pattern, now I'm looking for same here, same here, same here. And that portion of the limit will be 1. So let's see if we get that. Yes. This portion, and this portion are all the same. And they approach 0. Again, if I have here 4, the limit is not 1 of these. So where does this go then when x minus 1 approaches 0? Sine over, yes, this approaches 1. So then now we are applying the limit operator. We already discovered that this goes to 1. So let's apply to the rest and give me the limit. One over 3. So this is 1. 1 plus 2 is 3, 1/3. Very good. Awesome. Okay, so let's look at 52. Any questions on this, anyone? Okay, in 52, we have limit as theta approaches 0 from sine theta over tangent 7 theta. Okay, you can say, what's with this? Okay, slowly, same steps, no problem. Where is the numerator going?
Zero.
Good. What about the denominator?
Zero.
Good. So there is hope. No guarantee, but there is hope. Good. So we don't know how to differentiate this yet because we haven't talked about the difference quotient. We haven't talked about the chain rule, not the difference quotient. So we don't know how to do this yet. So here we could have differentiated, so to speak, but still we don't have one information that follows after this. And we are thinking in terms of sine over a quantity over the same quantity and the same quantity here. If I can emphasize this, I'm in business. So now I have limit as theta approaches 0. Sine theta is okay. Now I'm going to change tangent into sine 7 theta over cosine 7 theta because I know tangent is sine over cosine. I will flip because I divide by a fraction. So limit, do not drop the limit operator. We haven't applied it yet. Sine theta over sine 7 theta, and cosine goes to the numerator. Next to the fraction or the top, it doesn't matter. Good. So at this point, I have this piece, then I have this piece. But I'm missing something. I'm missing the denominator. This is okay, but I don't have this quantity, which is the same with these 3. Okay, that's fine. I can multiply and divide by it, because this is 1. So now, eventually, this piece will go to 1. Okay, so this is somehow resolved, multiplying and dividing by theta. This is 1, there is no problem. This is no ever an issue when theta approaches 0, because when theta approaches 0, where does cosine 7 theta go?
One.
Very good, awesome. So now, sorry about that. Now, we are looking at sine 7 theta. One thing that I did not say, and I should put it back in here, even if these two are switched, the answer is still 1. So limit as theta approaches 0, or x or whatever, of theta over sine theta, this is still 1. So these two will both give us 1. If it's sine x over x, or sine same quantity over same quantity, or same quantity over sine of the same, I still get 1. As long as this and this and this and this is 0, mandatory. Maybe I should have emphasized that from the beginning. This must be 0. If it's not 0, the answer is not 1. So 0 and all these three are the same, even if it's sine over the quantity or the quantity over sine, the same answer. We get 1. So then, what do I need? The problem with this is that I need a 7 theta over 7 theta. So there is no room here. I'm going to move to the next page and write this again. So which page am I on? I'm on 3. Okay, so limit as theta approaches 0. I already have the theta with sine theta over theta times 7 theta over 7 theta times sine 7 theta times cosine 7 theta. So I added this in, but it's theta over theta, which is 1. And I also added this in, which is 7 theta over 7 theta, which is still 1. I didn't change anything. This is 1, this is 1. But now I know, because theta approaches 0, when theta approaches 0, 7 theta also approaches 0, guaranteed. So this I know approaches 1. This I know approaches 1. This I know approaches 1. I will simplify 1 theta with another theta in the denominator. And then what is the final answer?
Uh, 1/7.
1/7. Great job. Any questions? Any questions?